Now, let us bring in the idea of time resolution and frequency resolution here. If we use bandwidth as a measure, please note as a measure of the range of frequencies that are emphasized by the function psi. Now, why am I saying once again that these frequencies are emphasized? Let me just recapitulate. I am saying this again and again because one must firmly understand this. I am saying that those frequencies are emphasized because in finding the dot product of a function x t with any translate of this function psi t or one of the stretched or compressed versions of psi t, Parsifal's theorem tells us that you are also multiplying the Fourier transform of x with the Fourier transform of that particular translate and dilate of psi, or for that matter phi, whatever it be. Now, we also understood that translation has no effect on the magnitude, dilation does, and when we multiply the Fourier transform of x by the Fourier transform of phi or psi as the case may be appropriately dilated, one is automatically emphasizing multiplying that part of the band which lies in the region of large magnitude of Fourier transform of phi or psi by a larger number, and the other parts are being multiplied by a tapering number. So, in effect there is a filtering operation also being done by phi and psi. Effectively, phi is doing a low pass filtering operation and psi is doing a band pass filtering operation. Let us make a note of this, this is very important. So, effectively phi is doing a low pass operation and psi is doing a band pass operation. Now, then it almost seems trivial. What is so great? We could have built a band pass or a low pass filter otherwise. Why did we have to do all this hard business? Well, you see, the beauty is in the two domains together, and this is where the whole catch lies, and this is where the whole struggle lies. You are able to do some kind of a crude low pass operation. I say crude because nobody will agree if you look at the frequency response, the Fourier transform of phi, that it is really very close to a good low pass filter, crude in that sense. You are doing a crude low pass filter operation, but with the proviso that you are also confining yourself in time. So, you are saying you are able to say with some confidence, and that confidence depends on how well localized that Fourier transform is around 0 frequency. So, you are able to say with some confidence that when I multiply x t by a certain dilate and translate of phi, I am emphasizing that band of frequencies around 0, which is covered by the appropriate dilate of phi. So, if you take phi itself and if you focus your attention on the main lobe of the Fourier transform, you may say in a crude sense that you are emphasizing the frequencies around 0 up to the extent of 2 pi, the main lobe goes up to 2 pi. And you are doing this in a time region in which phi lies. In fact, that can be sent non-crudely. So, phi is indeed very, very localized in time. I think nobody will disagree with that. So is psi. So, when you multiply by a certain dilate and a translate of psi, you are in effect doing a kind of localization in frequency around that point of maximum. As you saw, it lay somewhere near 2 pi, before 2 pi actually. And as you take different dilates of psi, you are taking different bands, and this is being done in the time zone covered by that particular translate. This is a serious statement we are making. We are making a statement about localization in two domains simultaneously, in time and frequency. And if you recall, in the very first lecture, when I introduced the subject of wavelets and time frequency methods, this is one of the things I mentioned as a fundamental challenge in signal processing. In fact, I went to the extent of saying the same challenge appears in different manifestations in different subjects. In signal processing, we see it as a conflict between time and frequency. Where is the conflict? The conflict is partly seen now, partly I say. You see, as you notice, in time we are very correct in saying that we have localized. After all, phi t and psi t and their translates and dilates are non-zero only over a finite region of time. So, localization in time in this case is not under question at all. It is localization in frequency which is somewhat suspect. We can crudely say that, because if you focus your attention on the main lobe, then in some sense it is localized. But there are these side lobes in the Fourier transform, both of phi and of psi. So, now we want to ask the question, what ideal would I like to strive towards? If I were to have my way, how should I make the Fourier transform of phi and psi look? We know how they should be in time. They should be packed into a finite region of time. We are able to do that. I would also like to pack them into a finite region of frequency simultaneously. Now, what would that region of frequency be? Let us use our understanding of signals and sampling a little bit here. You see, let us write down the dot product of x t with a particular integer translate of phi as a sampling problem now. So, if you take this product, if you wish, I can put complex conjugates. Maybe I should put a complex conjugate there. It would be a dot product in the strict sense. But even if I do not put a complex conjugate and confine myself to real functions x, I am doing rather well. In fact, we will do that for the moment, because we do not want to mix too many issues. Let us confine to real functions. And then I have this is of course equal from Parsifal's theorem to the Fourier transform of phi t plus tau times the Fourier transform of x integrated over all omega, and this is easy to evaluate. So, essentially we have a product of Fourier transforms x and phi, x cap and phi cap multiplied together, and then an inverse Fourier transform is being computed at the point tau. So, this is like even if you were to use a complex function, the only change would be here. You would need to put a complex conjugate there. That is why I said that is not such a serious issue at the moment. We will just focus on real functions and interpret. So, here when you multiply by phi cap omega, you are in effect doing some kind of a low pass filtering. And when you take the inverse Fourier transform, you are calculating what comes out of that crude low pass filter, whose impulse response is essentially phi, I mean. Do not worry about inversions or time inversion, it relates to phi, very closely phi. Now, what we are saying is, when you sample this, when you put tau equal to all the integers. So, if you take this and substitute tau by different integer values, when we sample at tau equal to n all integers, what is going to happen? We are going to take the original Fourier transform. You see, when we sample, if you take a function, let us say y t with Fourier transform y cap omega, and you sample this, sample ideally if you like, at all integers. That essentially means you are sampling at a sampling rate of 1. So, that amounts to taking the original Fourier transform, translating it by every multiple of 2 pi divided by 1, which is 2 pi on the angular frequency axis, and adding up these translates. So, let me write that down in terms of an algebraic expression. What we are doing essentially is, we are taking the original Fourier transform, translating it by every multiple of 2 pi divided by 1, if you please, every multiple of that, and summing up these translates. Some constant possibly, that constant relates to the sampling process. Let us ignore that constant for the moment, our attention is here. So, in order to reconstruct y from its samples, what should we have desired? We should have desired that these translates do not interfere with the original. So, it would have really been nice if we had been able to ensure that these carbon copies created by y cap omega plus 2 pi k are non overlapping with the original, and that is ensured by ensuring that the low pass filter cuts off at capital omega equal to pi. Let me sketch that for you. Had phi cap omega been an ideal low pass function, with a cutoff of pi, then this aliasing process would leave y cap omega unaffected. So, that is the ideal towards which we are striving as far as phi goes. Now, what is the ideal towards which we are striving as far as psi goes? Let us see. You see, when you go from V 0, which is what brought us to phi, to V 1, what is V 1? Just essentially V 0, but compressed by a factor of 2 in time, and therefore expanded by a factor of 2 in frequency. So, for V 1, I am talking about the ladder, MRA ladder, Haar ladder. we expand by 2 in frequency. We are talking about frequency domain behavior. So, we expand by 2 in frequency. That means, we are asking for a low pass filter with cutoff 2 pi instead of pi. Now, we also have an interpretation for the incremental subspace. Obviously, if V 0 is going to contain information between 0 and pi and V 1 is going to contain information between 0 and 2 pi, then the difference subspace W 0 should contain the information between pi and 2 pi. Simple. So, what we are saying in effect is psi is aspiring to be a band pass function between pi and 2 pi. And of course, this is for going from V 1 from V 0 to V 1. When you go from V minus 1 to V 0, you use a corresponding dilate of psi, which is aspiring to be a band pass function between pi by 2 and pi. When you go from V 1 to V 2, then you bring in a dilate of psi, which aspires to be a band pass function between 2 pi and 4 pi, and so on.